I will start with the previous study, which we published last summer, where we showed that skull is a bone, is flat bone, has bone marrow, and we showed that this bone marrow provides immune cells to underlying borders of the brain during physiology. And if the brain is sick or damaged or injured, or maybe tumors are growing there, or Alzheimer's pathology is going on there, these immune cells can even go directly into the brain and maybe, try to deal with the problem. So that was a previous study. In this study, we showed that the communication doesn't only go from skull to the brain, it also goes the other way. So if the brain is injured and needs this immune support, it calls the immune cells, and it does so by releasing molecules into the cerebrospinal fluid, which then goes through those unique channels, which have been identified by other groups. And they are ossified structures that connect the skull to the underlying brain. So CSF goes up and then reaches directly the bone marrow niches and delivers the message there. So for example, in the case of central nervous system injury, like spinal cord injury, when the system needs immune cells to come and clear the debris, the system, then damaged brain or spinal cord will release molecules into the CSF. CSF will go into the bone marrow, and then will recruit the immune cells. Then we'll go back into the injured site to try and resolve the problem.
The most fascinating concept was our first observation, actually. And so the finding that CSF, which is this fluid that kind of surrounds and ensheides our brain, can kind of directly access the skull bone marrow. And we showed the impact of this finding for neuroimmune interactions in spinal cord injury and meningitis. But this really simple observation has kind of many implications for different disease states in the brain. And so because the CSF is continuously exchanged with the interstitial fluid of the brain, it can kind of effectively mirror the functional state of this tissue. And so in diverse conditions, we have alterations in brain pathology, and these are reflected by the kind of alterations in the CSF composition. And so our findings kind of suggest this fascinating idea that these brain changes will also be sensed by the skull bone marrow to generate local immune responses in this niche. And actually targeting or kind of manipulating this axis could have really exciting implications for diverse neurological disorders.
The main goal we had for this study was to really understand how the central nervous system communicates with the skull bone marrow niche through the CSF axis. And so in order to really convincingly show that this axis was functional, we focused on really acute manipulations of the cerebrospinal fluid and looked for acute dynamic changes in the surrounding bone marrow niches. And one thing that we need to consider is that a lot of the neurological diseases that we're really interested in learning more about and solving, changes to the CSF composition happen on a far more chronic time scale. And so really understanding how changes in CSF composition over the lifespan or even decades impacts the skull bone marrow niche is something that really warrants focus moving forward.
As Jose alluded to, most of the time, brain diseases take a long time to manifest. But we're becoming increasingly aware through things like CSF biomarker studies that there are shifts in the CSF composition over the course of these diseases. So I feel like our study really adds some further relevance to these findings, indicating that these changes in the CSF composition in brain diseases might be able to shape immunity at the brain's borders. And we're very excited to see how these shifts in the skull CSF axis might influence diseases such as Alzheimer's disease, neurodevelopmental disorders, as well as brain tumors.